సార్ అది బిజీ ఉన్నట్టున్నారు. స్టార్ట్ చేద్దునా?
అవును సార్, అవును సార్. చేయండి సార్, స్టార్ట్ చేయండి సార్.
ఓకే, సార్ని ఇంట్రడ్యూస్
ఓకే సార్.
చేసి స్టార్ట్ చేస్తాను. ఓకే ఓకే. గుడ్ ఆఫ్టర్నూన్. గుడ్ ఆఫ్టర్నూన్ ప్రొఫెసర్ Umamahesh గారు, అండ్ థ్యాంక్ యూ వెరీ మచ్ ఫర్ యాక్సెప్టింగ్ అవర్ రిక్వెస్ట్ టు డెలివర్ ఏ lecture on urban floods under changing climate. It is the second day we are running this program. Yesterday we have three sessions. Today this is the fourth session of this day, and there are about nearly registered participants are nearly close to 800. And so now it is my privilege to introduce Professor Umamahesh garu to all the audience and participants. So Professor Umamahesh garu Nanduri, he has done is a BTech Civil Engineering from Osmania University and MTech in Water Resources Engineering from IIT Kharagpur, and a PhD from REC Warangal. He did PhD in optimal planning and operation of irrigation reservoirs under multi-crop environment. So he has been there in the National Institute of Technology since 1995 as a lecturer. Then now the present position is a professor, and he is also the visiting faculty at the Asian Institute of Technology, Bangkok during 2007 to December 2007. Professor Umamahesh garu, I was also there for the one session in 2011, August to December 2011.
Okay, that's good. Okay.
I was the visiting professor in WEM, Water Engineering and Management.
Yeah, okay, I was also there only, yeah.
That time the Professor Babel was there heading the division.
Yeah, okay.
Morning we have a Sangam Shrestha from WEM.
Yeah, I saw the schedule, yes, he has got lecture, yes.
Yeah, he was there. So sir is a visiting professor there in IIT Bangkok. Normally this visiting professor comes from the Ministry of Higher Education. It's deputation from the MHRD. So sir has areas of research interest is reservoir operation and management, hydrological analysis and modeling, irrigation management, watershed management, water resources system, water quality modeling and management, RSGS applications, neuro-fuzzy applications in water resources. Yeah, he has been teaching in the NIT Warangal various subjects: fluid mechanics, engineering, hydrology, irrigation engineering, system analysis in engineering, and computational methods, applications for soft computing. He has guided 10 PhD scholars till now completed. 8 PhD scholars are working now with him. He has almost guided 90 MTech theses. He has publications about 35 national, international journals and 50 international conferences. He has also done major research projects, completed few, and is also going short and medium range flood forecasting system for Godavari River Basin. It was sanctioned in 2018 August. So second project is decision support system for climate change adaptation in chain tank systems of semi-arid region. And he has also done a project on integrated water management model for BIS countries under climate change scenarios. Then real-time flood forecasting using SWAT model, MHRD Spark program. Integrated urban flood management in India, technology-driven solutions, which is ongoing project. And developing a suitable pedagogical methods for various classes in intellectual calibers. And Warangal Watershed Development Project sponsored by the Ministry of Rural Development, Government of India through District Water Management. So yes, sir has organized several workshops and short-term programs and this related to the water resources. She is also sir is also administrative responsibilities and chief warden, head department of civil engineering, dean students, dean planning, and coordinator TechU. He has also got award merit certificate for the paper presentation and international R&D session. And then state level Jalamitra award given by the government of Andhra Pradesh for successful implementation of watershed project, and GM Navate award for the best paper presented National Conference on Hydraulic Water Resources Hydro, best paper award for international conference on modeling tools. Then best engineering faculty award presented by the NIT Warangal and NIT Warangal Alumni Association. So these are the sirs, Professor Umamahesh, Professor Umamahesh, credentials of the Professor Nanduri V. Umamahesh. So now I request Professor Umamahesh garu to continue with the lecture.
Yeah.
Yes, sir. Over
Good
to you,
afternoon to
sir.
all the. Okay.
Sir,
Thank you, Professor.
yeah, sir.
Yeah.
Dr. Jairam Reddy is there on the line. He is the Chief Executive Officer, Science City, Andhra Pradesh.
Oh, hello, sir. Good afternoon.
Sir, good afternoon, sir. Hello, sir.
Good afternoon. Good afternoon.
Sir, this program is co-convener for that.
Yeah. Okay. Okay.
Okay.
That's
Thank
good.
you, sir.
Yeah.
Shall we go ahead, sir, now? Yeah.
Yeah. Okay. So good afternoon to all the participants and the organizers. And at the outset, I thank the organizers for giving me this chance to uh, share my views on in this program. In fact, I congratulate the organizers for taking up this program. And then when I see the schedule, I see a lot of top experts are there from across the world. And I think already you have heard Professor Nagesh Kumar from IISc Bangalore, then Sangam Srestha from IIT Bangkok. I think yesterday, you also had a meeting, lecture by M.K. Srinivas, who is the chief engineer of Krishna Godavari Basin and of CWC. And I think I really appreciate the organizers for bringing out such uh, top people from across the world for this, say, workshop or this course. Uh, okay, so going to my topic. Hope my screen is visible to all of you. The PPT.
చరణ్ గారు పీపీటీ ఒకసారి చూస్తా. చరణ్ గారు పీపీటీ ఒకసారి. చరణ్ గారు పీపీటీ ఒకసారి పెడతారా? చరణ్ గారు, చరణ్ గారు, హలో. హలో సార్, జయరామ్ రెడ్డి సార్, ఒకసారి చరణ్ గారు పీపీటీ ఒకసారి పెట్టమని.
ఓకే సార్. చరణ్, హలో చరణ్.
చరణ్ గారు ఒకసారి పీపీటీ ఒకసారి పెట్టేసి. చరణ్ గారు, హలో. హలో చరణ్ గారు, పీపీటీ స్క్రీన్. అలాగే 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 అలాగే, రైట్ రైట్.
I think it's visible now.
sir, but your video is not visible. PPT is visible.
Okay, I don't know whether how I share both of them.
Um, చరణ్ గారు సార్ వీడియో రావట్లేదు. హలో చరణ్ గారు. హలో చరణ్ గారు. హలో హలో చరణ్ గారు.
Okay, I think now both are visible. Hello.
Sir, we can see you, sir.
Okay, okay, I can continue. Is it?
Yeah,
Okay.
It is visible now. Please go ahead.
Okay, okay. Okay, so what I'm going to talk about today is urban floods under changing climate. I think you already heard about the climate change, its impact on water sources from various speakers already. And one of the important areas where the climate change is going to significantly have an impact is, as maybe knowing, floods. So, but I'm not going to talk about general floods. I'm going to speak about more of specifically about urban floods. So, now all of us know that floods are the biggest, severest natural disaster that we face every year. And in fact, across India, I think a lot of places every monsoon we hear about a lot of floods, and then how the floods affect the population as well as the property. But what we are talking about is a flood which till recently was not at all taken significantly. This is what we call as urban floods. Urban floods, when you look at when we compare this urban floods with what we talk about as a riverine flood or river flood, it's in fact a small event. But what you observe every year, most of the major cities, many cities, is just a 10 minutes heavy spell of rainfall. You see a lot of areas in the city getting inundated or flooded. And this, if you look in terms of volume of water that is coming as a flood, it's not as high as in a river flood, because say it's a smaller volume only when compared to what a river carries. And it usually occurs in a very short period, and uh, at can inundate a large area, but again, it's not spread over large, like a river flood. It just spreads over a certain region and for a very short period. But why it has become a significant is, say in an urban area, we all know that the population, we have a high concentration of population, and then a large, huge property. So every year, this floods in urban areas are causing a significant property loss, and also are affecting the normal life in a city, even if it's for a short time. So this has become an important issue across say the world, and especially in India, because most of cities maybe the reason being the way we plan the cities. we are not taking care of the drainage system properly, and thus you find that many cities are affected by floods. So in fact, I show some pictures. These are some pictures that you see commonly in most of cities, especially during monsoon season. And we can understand if this kind of situation occurs in a coastal city, like for example, Vizag or Chennai or other cities. But what the pictures that I'm showing here are all for Hyderabad. Maybe some 15, 20 years back, if people talk about floods in Hyderabad, maybe would have laughed. But today, this has become a common feature. If you see every monsoon, several areas across the city of Hyderabad getting affected by this kind of floods, and large areas getting inundated. And these are the pictures that you see. These pictures were taken from a flood that occurred in August 2008. But this is a recurring feature because August 2009 have taken specifically because it's one of the severest flood event in Hyderabad that has occurred in its history. But you find this kind of situation, if not so severe, but still this kind of pictures you see almost every year, say people getting affected because of floods. And all of us know about the floods that occurred in Chennai in 2015, one of the very severe events that occurred in the recent past in urban areas. And the impact of this flood, I think, is being felt in Chennai even today. Uh, so, what are the possible reasons for these floods? Why these cities have become areas prone for floods? This is a concern that we have. Now, if you look at the causes that cause the for urban floods, one is the natural cause. The rainfall, we have heavy rainfall. That's what happened in Chennai. In fact, Chennai received a very, very heavy rainfall in 2015, and that was one of the reasons of that kind of flood in Chennai. So, and the other thing that is observed is the frequency and intensity of this rainfall, heavy rainfall, extreme rainfall in cities is increasing over the recent years, mainly because of climate change. Apart from the natural causes, there are a lot of human causes. I just listed some of them. One is urbanization. We are, say, our cities are growing very rapidly and without proper care of the say hydrological system or the drainage system within the urban area. So urbanization, one of the major this thing, and the process of urbanization, we are encroaching the water bodies. Like what is happening in Hyderabad is one of the major reasons why Hyderabad is fighting that kind of floods is Hyderabad used to have lot of small lakes in several areas, but most of these areas water bodies are getting encroached and then they are being built up. So this is you are preventing say the natural water bodies where the water is going to be stored, and then thus this water has to go somewhere else, and thus it starts inundating our areas. And then most of drains are silted, clogged, and they're not properly maintained. And then the lot of deforestation taking place. So there's all various causes or say reasons why we have such kind of floods occurring in urban areas. You take any city in India, I think these floods have become a common a problem across all the cities, whether it's Chennai, Mumbai, Hyderabad, Bangalore, Delhi, and so on. Now, but my focus in this particular lecture would be on two important causes of urban floods. Uh, One is the increase in frequency and intensity of rainfall, heavy rainfall, extreme rainfall due to climate change. So I think already you have heard the different speakers speaking on the impact of climate change. So I'll focus on how this climate change is going to influence the intensity of extreme rainfalls in urban areas. Or maybe in general, actually, I'll say not necessarily urban areas. This obviously is going to increase, have an impact on extreme rainfall across the country, but we'll focus on urban areas. Another major issue is urbanization. So I'll focus on these two issues and how this two urbanization as well as the say climate change are affecting the urban floods and why the frequency of urban floods is increasing across all the cities in India. So this is the focus of going to be a focus of my lecture. But before I go into the main theme of talking, I just want to show some pictures. So it's not say basically most of the urban floods, I think, say the major reason is the human made, because this is how the condition of most of our drains are. So these are supposed to carry the storm water. And you see, any city could. I'm just not naming the city. I just randomly took some pictures. So this all these pictures show how we maintain our drains in our cities, and this obviously will add to the problem of floods. So not only we have increased, say, instance of extreme rainfall. At the same time, we also, because of urbanization, there's an increase in flooding. But to that, this condition of drains is another aspect which actually is causing more floods. With this background, let me first talk about the urbanization. Okay. I understand all the participants are basically have a background of civil engineering, and you would have studied the course of hydrology, and you know hydrological cycle and other things, the basics of hydrological cycle, and how the rainfall now process and all those things. So if you look at our cities, this is how the cities are growing. We are making them into concrete jungles. See, it could be just a picture of any city, any major city. It could be Hyderabad, it could be Delhi, or it could be Visakhapatnam, it could be Mumbai. So that's how the city is growing, and then you find it's completely a concrete jungle with very little greenery, and then completely constructed very high densely structures like this. So this obviously has an impact on the hydrological cycle of that area, because we are interfering to the natural drainage system of the area. This area had certain hydrological characteristics. It has got its own drainage conditions, and then whenever rainfall occurs, it has its own natural system which will drain the area. But what we did now is we have interfered into this, and then we have made this into a concrete jungle like this. So what's the impact of this? This is something which of all of us know. This is something which is talked about in various high textbooks of hydrology. So if you see here, this is, say, maybe this could have been the hydrograph of the flood when before urbanization. But what is happening because of urbanization? So you find that the peak is increasing. Why is the peak increasing? The reason is you have reduced the infiltration. Say, we completely paved the area. We made it into a concrete jungle. We have completely paved the area. So the infiltration got reduced. So because of reduction in infiltration, obviously there'll be more volume of runoff, and thus there is an increase in the volume of runoff. And then uh, because surface is paved, the water can flow more easily, and then velocity of flows will be higher, and thus it will reach say peak much faster. So you find that this will be the modified hydrograph in the urban area. So same rainfall without urbanization, this would have been the say the hydrograph caused by the rainfall, whereas because of the urbanization, the hydrograph gets affected, and this is how what happens after this thing. So you have a lower base flow, then higher peak, and shorter time to peak, and then increased volume. Total the volume of runoff itself has increased, and then okay, this is what happens from hydrological cycle point of view. Because you have modified the hydrological cycle, these are things that is happening. But uh, again, I'm not going to talk about all these things because it's all what you learn from hydrology, or you can develop a hydrological model and find out what is the impact, what happens after rainfall occurs, and how the urbanization has impacted the runoff, and then how much runoff is generated. But what is happening is, in addition to this, say, modification of hydrological cycle, the urbanization also is causing more frequent uh, uh, such events occurring. So it means the urbanization not only is influencing the hydrological cycle, but is also influencing the occurrence of extreme rainfall events. Why and how? This is what is happening in an urban area. Uh, so this is there is increase in precipitation intensities because of urbanization, and that is known as urban heat island effect. Okay, let's say this is this area. I hope when I move the pointer, all of you are able to see the pointer and then understand what I am speaking. Hello? Okay. So this is an urban area. So this area is getting urbanized. So what's happening because of the urban area? Now this area traps heat. This because completely it's a concrete jungle. So it's all you have built concrete and then paved area. So what happens is this area traps the heat. So when compared to surrounding areas or non-urban areas, the heat here is more, and thus it creates a situation called heat island. So what happens because of heat island is the temperature here is very high. So when wind is moving from here towards through the area like this, maybe this heat island would not be there. The wind would have traveled normally, but because of heat island here, this wind movement gets affected. And say obviously because of the high heat here, this cold air that's coming from other side will actually mix with this, and there'll be more convection taking place in this area, and it could cause more rainfall in the downstream locations of the wind. So this is how the temperature, for example, this red graph here shows the temperature plot across this area. So you find that in the center, this major city portion, the temperatures are very high, and then when compared to other areas. And so this is what you call as heat island. And this is obviously expected to cause more rainfall or modify the meteorological phenomena here and can modify the precipitation occurrences in this. So this area is likely to get more rainfall because of this. So the urbanization, so one aspect we are talking from hydrology point of view, because of urbanization, for same rainfall, we are likely to get more runoff. But the rainfall itself can increase because of the urbanization, mainly because of this heat island effect. So, so what is the effect of this heat island? It causes a change in circulation pattern of the air. So as the air moves, say this city area will obviously modify the circulation pattern. So the wind, so that can cause a change in the rainfall because of the intensification of convective precipitation. Because as you all know, when the cold air rises up or the hot air rises up, because this area has very hot air, when it rises up and the cold air comes here, it will have a lot of moisture, and that moisture will move downwards and will cause precipitation. So the heat island will cause change in circulation pattern and then intensify the convective precipitation, and then it can also cause local variation monsoon rainfall. So a lot of studies are done across the world on these aspects, but we try to do a study in the city of Hyderabad and see what happened in Hyderabad. Okay, so this picture shows how the Hyderabad has grown over the years. So these graphs here are actually the land use maps that we have got from satellite imageries. This first one here is 1972, and then the last one here, the top one, is 2013. Actually, what we have placed in reverse chronological order. So this is 1972 to 2013. So this red shaded area that you find in these maps is the built-up area. So if you look in 1972, this was the extent of Hyderabad. So just this is those who know Hyderabad, those who are familiar with Hyderabad, maybe they know that this is Hussain Sagar Lake. So Hyderabad was mostly Hyderabad, and this is Secunderabad area. This is Hyderabad area. This is mostly on the this east side of Hussain Sagar Lake only. The other side was not so developed. So this is how this was spread. And slowly over the years, you see the spread red is increasing. The spread of this red area is increasing, and this is what is in 2013. Okay, we started this study in 2013, around 2013-14. So I have pictures only up to 2013 here. Maybe if you take the pictures today, it maybe have gone further. So the built-up area, so this is all the red area is the built-up area. So you see the built-up area is where a lot of construction has taken place, a lot of buildings have come up. So this is spreading, so say rapidly from 1972 to 2013. Now, if I plot this total built-up area against time, this is what we get. So you see, this is 1972 and this is 2013. Now, what we observe here is between 2000 to 2013 or 2013, the increase is more rapid. In fact, here it is, if you look at the slope of this graph, it is gradual here, but it has become more and more steep as you from 90s to 2000 onwards. And we all know Hyderabad, why it has grown so rapidly over from after 2000. mostly because of IT sector, and a lot of industries have come up, and then say in fact all these areas are the new areas that have come up because of the growth of IT sector, the high tech city and all those things. This are, it is going towards this side. So you find this is how the city has grown. So there's a rapid expansion of city. In fact, I think if you do this kind of analysis for any city, most of the major cities in India, I think there's similar kind of thing maybe you may observe. Maybe you can take up, someone can take up a study like this for Vizag or some other city. Maybe you find a similar kind of pattern. There's a rapid increase in the urbanization because of various reasons. We have a lot of reasons that we can discuss, go on discussing on why the urban areas are growing. But this is what is happening in most of cities. There's a rapid increase in the level of urbanization. So what's the impact of this on the, say, rainfall in Hyderabad city? That's what we wanted to study. So we just started with a small preliminary study. We took the gridded rainfall data from IMD. These are the grid points that you observe here in this. These are grid points from where we have taken the rainfall. I think all of you know that IMD, you can get actually gridded rainfall data from IMD at different, say, these things, grid sizes like 0.25, 0.5, 1 degree, so on. This is 0.25 degrees gridded rainfall. These are the points. The center of city is located the sixth grid point. This is where city is mostly located. And then city is, as you have seen the previous picture, city is going in this direction, towards this direction, maybe in the northwest direction. Okay. Now, what you observe here is, say, I think green areas represent higher rainfall, and then this red shaded areas represent less rainfall. So if you go towards this, I think these are the areas which receive more rainfall, but that was around 630. What we did is, based on the rainfall data that we have, we split into two parts. One is from 1971 to 81, and then other one is from say from 97, 96 to 2007. Means first 10 years part that we had, and then the last 10 years that we had, and then we segregated these grids into rural and then non-urban and urban areas. So we plotted the rainfall, the total average rainfall, monthly rainfall over the 12 months at both, say, both urban areas as well as urban areas. The red line shows the average rainfall, average monthly rainfall over this 10 years period in urban area, and then the green line shows the average rainfall in the non-urban areas in the for the 10 years period. So this is the first 10 years period, 1971 onwards. This is from to 2007. So what you observe in both the cases is, okay, if you mainly the monsoon starts from around June, that's 6 month, and then extends up to around October. So this period is the time when the rainfall is high. So during the monsoon season, so there's obviously a difference between urban area and the rainfall in the urban area and then non-urban areas. You find even earlier also the urban areas were getting more rainfall than non-urban areas in this part, but you see the difference has increased. So see the non-urban areas actually say in fact urban areas during this monsoon season is having more rainfall, and thus there's the difference has increased. And basically, if you look at this peak of the green, you find that it's same in both the cases. Only what you find here is this has increased. So the difference has increased not because the rainfall has started decreasing in non-urban areas, but basically because the rainfall in urban areas has increased. So this is one observation that we made. Okay. And other observation that we did is again we plotted over three time slices. Okay, 1970 to 1980, then 1982, and so on, like this. Okay, so if you again say this is Hyderabad, as I said earlier, sixth grid point is the Hyderabad city. So if you look at the pattern of rainfall here, you find that okay, earlier also you find the distribution of rainfall was like this. This area was receiving more rainfall, and then as you move away towards the east side, the rainfall received was less. But if you try to see the change in the pattern of this distribution of rainfall over the space, you find that this high rainfall area is now concentrated around this grid point 6, and earlier at least the eastern the western side of the city was also getting rainfall, so these areas were getting more rainfall. But you see that this has changed. Now this portion is now concentrated more around this area of 6. So, and then if you look at the total rainfall also, it was 0.75 as the peak rainfall there, it is meters, and then it has become to 0.806 in the latest recent past. So, this is how the pattern of rainfall is changing. That means it shows that yes, the increase, the urbanization in and around Hyderabad is causing a change in the pattern of rainfall. Now I'm showing only non-monsoon rainfall here. A similar pattern we observed monsoon rainfall also. What I've shown here is non-monsoon rainfall. Okay. So there is a change in the pattern of distribution of rainfall, and the reason that we try to attribute here is the urbanization. So we just wanted to study further on this, and then especially we are interested as the talk the focus of the talk is on extreme rainfall and urban floods. So we try to look at the certain indices which we use to actually measure the extremity of rainfall. The first one is what is known as SDD2, which is ratio of annual precipitation to number of wet days. Okay, the total rainfall that occurred in a year by the total number of rainy days. What I mean by wet days is days in which rainfall, a significant amount of rainfall has occurred. So ratio of annual precipitation to number of wet days is what is known as SDD2. So there is a increasing trend on this in this index. I'll call this as index. Now, what does index indicate? Now, if you take the ratio, that means this is actually, I'll say, this ratio gives you approximately average rainfall on a rainy day. So what we observe here is between 1971 to 2013, there is a gradual rising trend as far as this SD2 is concerned. That means there's an increase in the the average rainfall that occurs over a typical rainy day. The reason could be, say, either the annual rain precipitation may be increasing or number of wet days can be decreasing. Now, what we observed as far as based on data that we have studied is there's not much significant change in the annual precipitation. Okay, it has increased slightly in Hyderabad city, but the number of wet days is decreasing, in fact, and that's one of the reasons why this SD2 is actually increasing. The second one is number of days a year when the rainfall is more than 20 mm. So just it's a number count. How many days the rainfall was more than 20 mm? Okay. Again, if you look at this graph between 1971 and 2013, you again find there's a trend. This dotted line shows a trend. There's obviously a statistical variation, but you find within this we observe there is a trend, increasing trend. That means number of days on which rainfall is more than 20 mm is increasing over this year. So it means this also indication that the extreme rainfall is increasing. The third index that we talked about is what is known as R99P, which is the we take the days on which the rainfall, like if you do a statistical analysis of the rainfall and rainy days, we take the 99 percentile days. That means 99 percentile rainfall, which is if I take daily rainfall has a statistical distribution. So if I take 99% value, means possibility that that rainfall will be more than that only 1%. So if I take such value and find out the total annual rainfall which occurred from these days where the rainfall was more than 99% value. So if I count that days, that is what we plotted here, and you find that also there's an increasing trend. And the last index that we talk about is maximum number of consecutive wet days. Okay. Incidentally, in this case, we find there's a decreasing trend. The number of consecutive wet days is decreasing, while all other three indices are increasing. So all this, in fact, these are the standard indices that are used actually to measure the extreme rainfall in a particular region. So these indices indicate the extent of the distribution of temporal distribution of rainfall and how it is changing. So these indices indicate that there's a change in the temporal distribution of rainfall, and thus the extreme rainfall is actually increasing in the city of Hyderabad. Okay. Another analysis that we can perform here is what is the distribution of rainfall over a day, what you call a diurnal distribution. So if I take the rainfall over the 24 hours period, in fact, you find again that we divide this total period into two time slices. 1971 to 80 is the first 10 years period that we have taken. 2004 to 13 is the last 10 years period that we have taken. And what we did is we plotted the first two indicate the how the total rainfall is distributed over the day. So this is for monsoon season, and the second one is for non-monsoon season. So this dashed line is for the first 10 years period, and over the last 10 years period is this one. What again we observe is that uh, the rainfall distribution pattern also is changing. That means if you see there's more instance rainfall occurring late night hours or early hours of day. And if I express this in terms of percentage, so the percentage basically you find that in the evening hours, 8 o'clock onward, this change is significant. Means the distribution of rainfall, temporal distribution of rainfall, you've observed there's a pattern now. During the, say, like, uh, say monsoon season, say maybe the monsoon season, there's not much change, but during the non-monsoon season, what you find is there's more occurrences of the heavy rainfalls or rainfall events during the evening hours than during the other hours of the day. So, and you know, most of the time, say evening hours causes more disturbance because the time when a lot of traffic will be there, and then you find could be a cause of traffic jams and all these things. This is something which we frequently observe in the city of Hyderabad. Okay. So all these are some preliminary analysis that we have tried to do in order to understand how or to find out whether there's an impact of urbanization on the rainfall pattern in the city of Hyderabad. And then we try to quantify this because there's all a qualitative kind of analysis. Obviously, we need to do a more detailed analysis to quantify the impact of this on the rainfall, extreme rainfall. So this graphs actually we did a trend analysis of rainfalls of maximum rainfall of different durations. Again, all of you you would have studied hydrology. In hydrology, we do extreme value analysis. And extreme value analysis, one of the methods that we use is what you call as annual maximum method, where we pick up the maximum from each year. So the same thing we did here. I have the total daily rainfall in the city of Hyderabad. So I picked up like what we collected data that we have collected is hourly rainfall from the city of Hyderabad from 1971 to 2013. And so we pick up the annual maximum of 1 hour intensity. That means if we take all the 1 hour intervals over the entire year, we pick up the largest rainfall that occurred in a given year. So like this for all the years of 1972 to 2013, we picked up and plotted that as a time series. And this is that graph. Similarly, we picked up the annual maximum rainfall of 2 hours duration, 3 hours duration, 6 hours duration, 12 hours, 18 hours, and so on. And these are the graphs that we have plotted. And then we use a simple technique called Menkendahl test. Again, those who are familiar with the statistics, you know, Menkendahl test is used for, say, doing trend analysis or finding whether the trend is significant or not. So it is a Menkendahl test. And this p-value indicates how significant this trend is. A very low value of this p indicates the trend is more significant. Except the first maybe 1 hour and 2 hours, to some extent 3 hours, all other values are low. And so there is, that means statistically there is an indication that this maximum rainfall at different duration, there's a significant trend in this say series maximum rainfall, and this tau indicates the slope. All the slopes are positive, means that the maximum rainfall is increasing, say increasing over the years. Now, how do we quantify this increase in the rainfall intensity? I think in hydrology, we talk about what are known as IDF curves, which give the relation between intensity of rainfall, duration, and frequency of rainfall. You all know that the maximum intensity of rainfall decreases with the duration. A longer duration rainfall is supposed to have a lower intensity of rainfall, whereas short duration rainfall is expected to have a higher intensity. So the intensity of rainfall obviously is a function of duration. So as the duration of rainfall increases, the intensity, average intensity of rainfall, the maximum intensity of rainfall starts decreasing. And then say because rainfall is something which is unpredictable, we use concept of probability and talk in terms of its frequency. So, and we know that high intense rainfall occurs less frequently than low intense rainfall. So we talk about the frequency of rainfall. So based on that, we develop relations between the intensity of rainfall, the duration, and the frequency. And this relation we plot in the form of graphs, which are called IDF curves. Where do we use this IDF curves? IDF curves are very useful in urban areas. Why I'm talking about IDF curves here is because basically they are useful in design of urban drainage systems. We depend on IDF curves for designing all our urban drainage systems. And also, okay, they're also useful for finding the peak discharge from small catchments. So, for example, designing small culverts or culverts across the national highways or railway lines, all these things. There also we use IDF curves, especially in small catchments where you don't have any flow data. In order to get the flow, we actually use the intense duration frequency analysis, and then from that arrive at the peak discharge by using what is known as rational formula. I think all of you have a background of hydrology. I hope you understand these terms more easily. So now what we wanted to do is find out what's the effect of this, both the urbanization as well as the climate change on the relation between the intensity, duration, and frequency. As our preliminary studies indicate that there is a change in the intensity of rainfall. For example, if I take the city of Hyderabad, we have done a study there, and we find that the extreme rainfall is increasing. Obviously, when I say extreme rainfall is increasing, that obviously has to influence the extreme intensity of rainfall also. So, how do we incorporate this in our IDF course? That's what we want to study. Just to give an idea about the intensity, say to make you appreciate our analysis, I'll just try to give some kind of brief background of frequency analysis. Uh, Maybe many of you may know this because you may be teaching hydrology to your undergraduate students, maybe many of your teachers or senior students. Maybe you have studied already hydrology and then you may be knowing all these things. I just wanted to just continuity sake for talk about this so that you'll be able to appreciate what we did for this IDF curves. We all use frequency analysis in hydrology to develop a relation between the magnitude of an event and its frequency. And mainly we use this frequency analysis for hydrologic extremes like rainfall, extreme rainfall, floods. Okay, mostly in hydrology, we study out flood frequency analysis where we talk about floods and then find out relation between the flood and its magnitude of its flood and its frequency in terms of return period. So it can be used for other extremes like droughts or extreme rainfall and so on. So in this, all these things, we use a concept of return period. What is this return period? Okay, let's consider an extreme event like say XT. So the return period, as maybe you all are aware, is the expected recurrence interval of the consecutive occurrence of this event. So if the interval between two consecutive occurrences of xt, if I say it's recurrence interval, the average of this recurrence interval measured over a long period of time is what we call as return period. So we use the return period like for 2 years, 5 years return, 5 years return period, 10 years return period, and so on. So when I say a 5 years return period flood, what I mean is a flood that is likely to occur once in every 5 years. That means it's likely to occur once in every 5 years means that on average it occurs once in every 5 years, but doesn't mean that if it occurred in 2020, it will not occur till 2025. Any given year, it has a chance of its occurrence is 1 by 5, means it has got once in 5 years, so 1 by 5.2. So any given year, there's a chance that that flood will occur with a probability of 0.2. So that's what the meaning of return period is. It means it indicates the average interval, recurrence interval between two consecutive occurrences of a a particular event of interest. So instead of talking in terms of probability, it's more easier for us to talk in terms of return period in hydrology, because we talk in terms of when we talk about designs, we design, for example, a culvert or maybe a storm drainage system in an urban area for a return period of 2 years. Means we assume that we are designing this for a flood event which occurs once in every 2 years, or maybe a bridge across a national highway may be designed for a return period of 50 years. Means if we are designing it for a flood which occurs likely to occur once in every 50 years. So means uh, so the risk that we take in a design depends upon return period. A larger return period obviously will reduce the risk. A small return period, because that's a small return period, it occurs more frequently, so there is a more risk involved. So we choose the return period based on the type of structure that we are designing, and then the importance of structure, and then based on that, we decide the return period. So most of the urban stormwater drainage systems are usually designed for small return periods like 2 years, 5 years, or 10 years, because they're all small structures, and then damage caused to them may not cause a very significant economic loss. Okay, so with this background, let's say uh, we what we are trying to do here in frequency analysis is we are trying to develop a relation between the magnitude of the event, whether it's rainfall or flood or drought, and the return period. To do this, I need to get the data of the extreme values. So how do we get the extreme values? For example, if I take rainfall data, now what we are doing is we are measuring rainfall continuously. For example, if I have a recording type rain gauge station, I may measure rainfall every 15 minutes, or every 1 hour or so on, and I have data over number of years. So if, for example, we collected hourly rainfall data for Hyderabad city from 1971 to 2013. So we have every 1 hour rainfall recorded every 1 hour over all this 42 years of data that we have. So this total data is what you call as a complete duration series. So I want to extract the say extreme events out of this. One way of collecting this extreme series is through what you call as annual maximum series. I pick up the maximum from each year, and so I have one event for every year. So it's annual maximum. So if I have 42 years, I have 42 years of annual maximums. So that becomes the annual maximum series. So I use that as extreme data and then do the study. But one limitation of this annual maximum series is when I pick up the largest from 1 year, the largest of 1 year, we are picking only one from each year. So largest of this year may be smaller than the second largest in another year. So that way I'm actually losing certain extreme events because of that. So the other way is you assume that, say, okay, you fix a threshold. So anything above the threshold, you consider as an extreme event. So if I consider the threshold and then fix a threshold and all, I'll take all the data which is above the threshold, and that series becomes what you call as partial duration series. Okay, it has got its own limitations. I think these are all fundamentals which we study in hydrology. I'll not go deep into this. So again, there's always a question of which one you have to use, annual maximum or partial duration series, and so on. And when you are interested in large return periods, I think it doesn't make a difference whether you're using annual maximum series or partial duration series. But when we're interested in small return periods, like for example 2 years, 5 years, that's what we do in urban areas, then partial duration series are better than annual maximum series. That's what the studies have indicated. Okay. And then, okay, one of the limitation of partial duration series is number of data points that you have may not be equal number of years. But if you pick up the threshold in such a way that you will have exactly, say, n number of values where n is the number of years of data that you have, then it becomes what you call as annual exceedential series. So these are the different ways, the three different ways in which you collect the extreme values and then do subject it to frequency analysis. Okay. So anyhow, in the case of Hyderabad, we did both annual maximum series as well as partial duration series, just for information. Other basic knowledge that all of you have is about distributions that we use in the hydrology. We use different types of probability distribution functions for doing this frequency analysis. I just listed three of them, which are very commonly used for this extreme value analysis in hydrology. One is what is known as general extreme value distribution. Okay, I think most of you are familiar with this, one of this general extreme value distribution, the second part that I have shown here, which is known as a Gumbel distribution. So actually at undergraduate level, when we teach the students frequency analysis and frequency analysis, we don't talk about a general extreme value, we just talk about only the Gumbel distribution. This is this part. Okay. Uh, Now, general extreme value is supposed to be a family of distributions. You find that the zeta, mu, and sigma are what you call as the parameters of distribution. X is the variable, and these are the parameters. This mu is called the location parameter. This is called the scale parameter, and zeta is called the shape parameter. So this is a three parameter distribution. So if zeta is equal to 0, then it gets converted into what is known as Gumbel distribution, or what you call an extreme value type 1 distribution. So there are three types of distribution depending on the value of zeta. So zeta is positive, equal to 0, and negative. Equal to 0 is what this is, Gumbel distribution, which is more popularly used in hydrology. Okay, so this is one of the distribution that we use very frequently in hydrology for modeling the extreme values. And other distribution, which is more popular in USA, is what is known as log Pearson type distribution. Again, this also has three parameters: the lambda, beta, and epsilon. And this is more popularly used in USA, as said, for flood frequency analysis. Then all of us are familiar with the normal distribution, but obviously none of our hydrology data are normally distributed. But we just use a transformed log normal distribution, what is known as log normal distribution, uh, which is again a common one. So we usually use one of these distributions to do the frequency analysis in the hydrology. The same thing is applicable for rainfall also. If I want to do frequency analysis of extreme rainfall, I can use one of the distributions. But recent past, it's more common to use this distribution, general extreme value distribution. So we don't confine ourselves to Gumbel distribution. We use general extreme value distribution. So obviously, you find zeta also based on the data that we have, and depending on data value, it could be a Gumbel distribution or it could be one of the other types of general extreme value distribution that we have. So as far as our study is concerned, we did use the general extreme value distribution. Yeah. Okay. So what is that we are trying to do those frequency analysis? So this graph shows a probability density function, how the probability density function varies. Okay. So I'm interested in finding out an extreme value. So like I want to find out xt, which has got a return period of t. If t is the return period, as I already mentioned earlier, uh, probability of its occurrence means probability that it will be equal or exceeded is 1 by t, that is p, 1 by t here. Okay, means if you all are familiar with probability density functions, mathematics of it, the area under the probability distribution function gives us the probability. So the left side area gives us what is known as probability of non-exceedance, whereas the right hand side area gives us the probability of exceedance. So in this case, we are interested in probability of its exceedance. So this green shaded area is what is probability of exceedance, and this is equal to 1 by t. So I'm interested in finding out the value of x, which has got a probability of exceedance equal to 1 by t, where t is the return period. So if I know the distribution, what it follows, then I can use this equation. This is for general extreme value distribution. Similarly, you can write down this kind of equation for other distributions also. I'm sorry, here there's a type mistake. It should be xt, not zt, xt. So this is how we find out p is the probability. So this is how we can find out what is xt. That's what we're trying to do in frequency analysis. So, okay, so I can apply the frequency analysis. How do we do it? I have rainfall data of Hyderabad city. So I pick up the annual maximum of 1 hour, annual maximum of 2 hours, annual maximum of 3 hours, and so on, and then do this frequency analysis. I take this data and then apply general extreme value distribution, find the parameters, the different methods of estimation of parameters, and then you find the parameters, and based on that, find a relation between the magnitude and return period. And using all these relations, this is how we typically plot the intensity duration frequency curves for Hyderabad city. So this graph gives us the relation between the intensity of rainfall against duration for different return periods. So the lowest, this blue line is for 2 years return period. The next one is for 5 years, 10 years, 50 years, and 100 years. So for a given duration, as you can see here, say for example, if I take 6 hours in duration, So the intensity of rainfall is increasing as we go for higher return periods. Now, again, same thing. If I take for a particular, say return period, let's say 2 years, as the duration increases, so you can see that the intensity of rainfall is decreasing. So this is typically how the IDF curves look like. So this is simple exercise that most of us learn in hydrology, where if I have rainfall data, I can do this analysis of rainfall data and then based on the develop the IDF curves. And you know how to use this IDF curve. So example, I want to find out for a small area, what's the peak discharge. Then we use a simple rational formula called CIA, peak discharge equals C into I into A. We see the runoff coefficient, I is intensity of rainfall and A is area. So intensity, what intensity should we take? I'll take the intensity of rainfall for the given return period. I'm designing the structure for the particular return period. So I'll pick up that return period. And then we find out what we call as time of concentration or the time for the, say, the runoff coming from the farthest point, the catchment to reach the outlet. And that is taken as the duration of rainfall. And for the duration, use this IDF curves to find out the intensity and substitute that intensity in the formula and find the peak discharge. So this is a method that is commonly used for finding the peak discharge in urban areas to design the urban storm drainage systems. Okay, but the question is now, as we have observed earlier based on some preliminary studies, the rainfall in the city is not stationary or it is changing because of various reasons. We'll see what are the reasons why it's changing. Then in that case, this relation is developed based on the past data. Now, is that the relation hold good for me to design a structure for the future? That's a question that arises. That the intensities may be changing because of climate change or because of urbanization, whatever the reason, there is a change. So, how is this change reflected in this IDF curve? This is what say we have to look into. Now, we try to do again a kind of a simple analysis. So we plotted the relation between intensity versus duration of 2 years return period, again for different time slices. Uh, this blue line here that is going center is for total duration of the rainfall data that we have 1971 to 2013. And then we divide this into three 14 years periods, that is 1971 to 84, then 85 to 1998, 1999 to 2013, and then plotted the same relation for these each 14 years. Okay, I'll say 14 years is a very small period for do the frequency analysis. So I say it's not correct for us to actually use only 14 years to do this. But just if you're curious to know, is the relation static? And what we observe here is the blue line here shows the total. But if you look at this, red line is for the 1971 to 84, whereas the yellow line is for the recent period. So you find that uh, if you compare the first 14 years to last 14 years, there is a change in the intensity for same duration and for same return period. That means there is likely to be a change in the intensity of rainfall for a particular duration for a given return period with time. So I cannot expect that these values remain static with time. Why are they changing? The change could be because of climate change or because of urbanization. So the intensity duration curves, like the basic assumption that we are actually using in this developing the idea of curves is we are assuming that this uh, uh, the distribution that the rainfall follows is stationary. But the climate change, urbanization, land use change, there are so many other factors which can change this, and thus the assumption of stationarity may not be correct. So that's the reason why we have to uh, uh, do what we call as non-stationary analysis of rainfall. So let me explain what this non-stationary analysis means. Okay. So this is what I explained just now. This is a probability density function. We assume that this remains constant, it doesn't change with time. And based on that, let's say I'm trying to find out 10 years return period level. And so what is that? 10 years means the probability is 0.1. So I'll find out the value of intensity of rainfall, which has a probability of exceedance of 0.1, which is 1 by 10. And let's say I found out this as 90 millimeters per hour. But the problem is I'm assuming that this distribution is stationary, but this distribution may not be stationary. This distribution could change. So if there's a change, for example, I showed a shift in the distribution. The shape and size of distribution remain same. They also can change, but I just, for the sake of explanation, I just showed here the same shape, but it just got shifted, let's say, towards the right side. It could be, it could have shifted to left side also. Let's say it's shifted towards right side. It means this probability density function will not remain same in the future. So in the future, it has shifted like this. Now, if I consider now the 90 millimeters per hour, in the new climate or in the new situation, its area has increased. The area on the right hand side of this 90 millimeters is not going to be more 0.1 like what you have here. It has increased. So this red area has increased the area. So what does this mean here? If this area has increased, means one, because we are calling return period as 1 by this area. Obviously, 1 by this area means the return period is decreasing. Means what we expect a 90 millimeters per hour, we expect to occur once in 10 years. Maybe it will occur more frequently in the change situation. So this is likely to happen. It can happen other way also. As I said earlier, if this shift is towards the left side, then maybe the return period could have increased. That means instead of once in 10 years, it could have occurred once in 10 years, 5 years also, once in 20 years or once in 5 years. So obviously, the concept of stationarity may not be valid under this changing situation. So climate change and other changes are influencing the relation, and that's the probability density function. So how do we incorporate these changes in our analysis? So as I said, first part is I'll try to explain the non-stationary, how we develop non-stationary analysis, and then later I'll talk about the climate change and how we take into consideration the effect of climate change. So I'm just taking an example of extreme value distribution because that's more commonly used distribution for analysis of extreme rainfall. This is what I have shown earlier. There are three parameters: alpha, beta, and k. Okay. So this is location parameter. This is, I said, scale parameter. This is shape parameter. I'm sorry, notation I think I've used differently here. Now we're assuming, when I say this distribution is constant, that means I'm assuming these parameters to be constant. But if I want to simulate the changes that take place in the distribution, maybe these values as parameters need not remain constant. I assume that the future also the same distribution is followed, but the values of these parameters may not remain constant, they change with time. So I'll try to express this parameters alpha, beta, and k as functions of time. So I've used the subscript T here to indicate that these alpha, beta, and k are expressed as a function of time. I just showed alpha. I'm writing this alpha as a function of time. I can write this as alpha naught into alpha 1 plus some function of time. Okay, some function of time. So what kind of function of time? There are two ways. So the parameters can either be expressed as function of time, or why is it changing with time? Because something else is influencing. There's some physical phenomena which is causing a change in our parameters. So if I know what that physical process which is affecting our rainfall here is, then I can use that instead of time. So I may say I may either express this parameters as function of time, or I may try to use them as a function of some physical covariate which is expected to influence the extreme rainfall. Now, as far as Hyderabad is concerned, we considered 4 different physical processes which are likely to influence the rainfall, extreme rainfall in Hyderabad. One is ENSO cycle. All of you know El Nino and then La Nino. These are the two phenomena which have a significant influence on monsoon in Hyderabad, in India. So there's a cycle. So we have taken the ENSO cycle. So we try to see whether this cycle has an influence on the rainfall, extreme rainfall in Hyderabad or not. Another process, global temperature anomaly. What it simply means is, okay, if I take the average global temperature, then there's always every year there's a difference in temperature from the deviation of the say average. So deviation from the average is what we call as global temperature anomaly, or these two are what you call as global phenomena. These are things that are happening across the world. Whereas I also consider two local phenomena. One is local temperature anomaly. Means if I take the temperature of Hyderabad itself and Hyderabad temperature and deviation from the average, the long-term average is what I call as local temperature anomaly, and then the rate at which urbanization takes place or the built-up area. So there's another parameter which can influence your extreme rainfall. So these are the 4 parameters which we consider. So what we try to do here is we try to express this parameter alpha or beta. We assume k to be constant because there are some studies which k is more sensitive. So actually, so usually when we do this kind of non-station analysis, we don't consider k as a function of time, but we consider other 2 parameters as a function of time, alpha and beta. So try to express them as functions of these 4 variables and try to see what is the influence of these 4 variables and which of them is more significantly influencing the. So what now we try to do here is the same distribution we are using the same process of frequency analysis, except that these parameters, alpha, beta, we are trying to express them as function of either NS cycle or global temperature anomaly or local temperature anomaly or urbanization, and then find the parameters. So instead of 1 alpha t, I am trying to find out 2 parameters here, alpha naught plus alpha 1 into NS cycle, or alpha naught plus alpha 1 into global temperature anomaly. So I'm trying to use one of them into this expression and try to find out its alpha naught alpha 1. With the same process, there are different parameters estimation. We use what is known as maximum likelihood method to estimate the parameters and then estimate the parameters and then do the same analysis. Except that in this case, this parameter is changing with time. So your frequency itself is changing with time. So for a same value, the frequency may be different at different times. So we took the 95% value and tried to compare with the historical values. So based on analysis, okay, if I divide this into 2 parts, short duration rainfall and long duration rainfall. Short duration rainfall like 1 hour, 2 hour, 3 hours rainfalls is more influenced by local process than global process. The urbanization and local temperature anomaly have more influence on the short duration rainfall and when compared to global parameters. And so that's what is happening as far as the short duration rainfall is concerned. Whereas if you take the long duration rainfall, like 1 day, 2 days, or 12 hours, 1 day, 2 days, etc., what we observe is the global process is more significant than local process. So means our study says that the short-term rainfall, a rainfall which occurs for a short duration like 1 hour, 2 hours spell of rainfall is more influenced by the local phenomena like urbanization or say temperature anomalies and local temperature anomalies and so on. Whereas a long duration rainfall, long-term rainfall, long duration rainfall like 1 day, 2 days, 3 days and so on is more influenced by the global phenomena rather than local phenomena. So this is how the say like the probability density function got shifted as far as the short duration rainfall is concerned. This is how this got shifted in the case of long duration rainfall, and based on that, we constructed what we call as non-stationary intensity duration frequency curves. Okay, so this it just shows typically. So here, just for a particular frequency, we plot the graph between intensity versus duration for both stationary as well as non-stationary, and show how the results are typically look like. Okay. So this is a relation for different written periods. This first one is for 2 years written period. This is for 5 years. This is for 10 years written period. This is for 25 years written period. So the red shaded line shows for non-station analysis, and the green line shows based on what we got based on station analysis. So all the graphs you find that this red line is above the green line. Okay. Based because the scale is small here, you may not find you may say there's not much very large deviation between these two. For large durations, the difference between becomes smaller, but when you go for small durations, difference significant. I've shown for just one duration. For example, if I take an extreme event with a written period of 2 years and a duration of 1 hour, the non-station analysis is given as a value of 53.86 millimeters per hour, whereas the stationary, based on stationary assumption, the intensity that we got is 42.85 millimeters per hour. So what's the difference? Almost 11 millimeters per hour is the difference. Now 11 millimeters per hour, you may say it appears to be small, But in an urban area, a rainfall of 11 millimeters per hour or 1.1 centimeters per hour is obviously a very, very significant change, difference. Okay. The same thing if I say, if I take for 5 years return period and 1 hour duration, uh, okay, same thing. So we got, based on station analysis, we got rainfall intensity is 52.26 millimeters per hour, whereas for based on non-station analysis, we got 60.85 millimeters per hour. Now, what we observe from here is, see, for example, if I design a urban infrastructure for a time period of 5 years and for a duration of 1 hour, okay, I will design the structure for, because if they use the conventional methods that we have been adopting, all our conventional designs, we would have designed this for 52.26 millimeters per hour of intensity of rainfall. Okay. Now, what is happening because of this, say, change in the intensity relations, intensity duration frequency relationship? The same intensity, or in fact higher intensity, is occurring more frequently. The same duration is same, but it occurs instead of 5 years, it's occurring now once in 2 years. That means the structure which is expected to fail once in 5 years, we expect this flood to occur once in 5 years, but it occurs once in every 2 years. So the infrastructure that you have designed, or the structure that you have designed, now has higher risk than the risk for which you have designed. So this is what is happening in one of the things that is happening in urban areas. We all designed the drainage system, but we designed for a certain frequency, but we are getting, say, a higher frequency more frequently and higher rainfall more frequently, and that could be one of the reasons why our structures or systems are failing more frequently. Okay, please note, here I just like to make a point here. So please note that the shortest duration that we have taken here in analysis is 1 hour. The reason is the limitation that we had. The IMD has provided only 1 hour rainfall data. Though they measure, it's a continuous rain gauge station, they have rainfall, they measure rainfall once in 15 hours, but when they store only 1 hour durations. But in urban area, in fact, many times we actually design for lower than 1 hour duration also, because our small catchments are very small. The time of concentration usually is 15 minutes, 20 minutes, and so on. So I need to have the intensity for such short durations. So if you go for a still further shorter durations, then in fact the intensities, obviously the difference between the intensities are going to be much more higher than what we find for 1 hour duration. Anyway, we try to do some disaggregation process and try to develop this thing and develop this. This is as a different study undertaken in a project. Anyway, I may not have time to discuss those things, but we try to use statistical methods to actually disaggregate this rainfall and develop the intensities for even shorter durations like 15 minutes intervals, 30 minutes intervals, and so on. So this aspect shows this is how actually we try to incorporate the impact of either global phenomena like climate change, global warming, or the local changes that take place because of urbanization into the say analysis through this idea of analysis. Okay, so what we are trying to here is what we are trying to assume that the distribution that the rainfall follows, the distribution that the extreme rainfall follows, is not stationary. It actually changes time, and thus we incorporate that in our analysis, and then assume the parameters of distribution to vary with time, and accordingly develop this what we call as non-stationary IDF curves. Please note that if you look back at the relation that we have shown here, these parameters are changing with time. That means every year you have different values. So each year I can find different intensity. But what we plotted is now I can actually have a construct a probability distribution function based on this values. That means I have 42 years of data, then I'll have 42 different values of this written, say for a given written period, 40 different values. What we took is, when I plotted this graph, what we took is the 95 percentile value. Okay, that's what we get. So otherwise I could have taken a different value. So if I take a smaller percentile or a higher percentile, maybe the values could be different. Okay, this is how we try to understand the impact of urbanization, and then how we try to incorporate that into the development of intense duration frequency curves. I'll very briefly talk about the impact of climate change also, because climate change I'm not going to talk about more detail, because I think already you had lectures, a series of lectures on the impact of climate change and water sources, and then I think the other experts would have talked about how to model the impact of climate change. What I am going to show you is how we use this modeling techniques actually to study how this climate change is influencing the, again, the same thing, intensity, duration, frequency curves. I'm focusing on intensity, duration, frequency curves because in urban areas, this is the focal point, because all our say designs depend upon IDF curves, and we don't have flow data, so we need to depend on IDF curves actually to get the flows. We need to use this for hydrology model along with the hydrology model to find out what will be the impact of the flooding in the urban areas. Uh, Okay, I think these are things that the other people would have talked to you. The impacts, so basically, in case of water sources, okay, there are many say impacts, but in the as far as rainfall is concerned, the climate is influencing the intensity, and frequency, and duration of floods and droughts. It means of all the extremes, whether it's rainfall or flow. Uh, there are changes in the climate is causing a change in the precipitation pattern. Climate change is causing a change in the precipitation pattern, and the change in the precipitation pattern is actually causing a change in the intensity and frequency and duration of floods and droughts. So we are talking about the floods here, and then because I don't have directly flood data, I'm trying to talk about the change in the intensity, frequency, and duration of floods in terms of the change in the intensity, frequency, and duration of the rainfall, extreme rainfall, even in urban areas. Uh, and to study the modeling of, say, to model the hydrologic impacts of this climate change, I think the other speakers in the morning would have, yesterday and today morning, would have talked about you what we call as global circulation models or global GCMs. And then GCMs are, there are a lot of GCMs developed by various climatology centers. And then one of the basic problems with these GCMs are they have at a very coarse resolution, and in hydrology we needed a finer resolution. And the other major issue with GCMs is GCMs are very good in modeling variables which are continuous, but variables like precipitation which are discontinuous are not properly modeled by GCMs. So because of these two reasons, we have to scale down these predictions made by GCMs. Now, GCMs are simulation models which are like basically hydraulic, say they are based on they're physically based models which are run on a global scale in order to understand the say the impact of the increase in greenhouse gases and emissions and other things. So we try to use this predictions coming from GCMs in order to understand the impact of climate change on hydrology. So at the hydrology scale, because we need a finer scale, we need to scale down from a larger scale of GCMs to a smaller scale. And this phenomena, I think all of you are familiar with, is known as downscaling. Uh, for downscaling, there are different methods of downscaling, and I think you'd have been exposed to this in the other lectures. Uh, basically downscaling techniques are classified into two basic categories. That is, one is dynamic downscaling, and then what we call as statistical downscaling. Most of the hydrology studies today, in fact, they use statistical downscaling for obvious reasons. Statistical downscaling requires less computational effort, whereas dynamic downscaling requires huge computational effort. And only few centers like IITM in Pune, Indian Institute of Tropical Meteorology in Pune, and some other centers are able to do the dynamic downscaling. But most of we say researchers who do studies, because we don't have that kind of computational facilities, obviously we focus more on statistical downscaling. But statistical downscaling techniques have their own limitations. So what we did here is we have the hourly rainfall data from Hyderabad city from 1971 to 2013, and we collected output from 24 GCMs under different RCPs. I think all of you know what is this RCPs also, different scenarios, climate change scenarios that you have for future. Among the different downscaling techniques, we try to use a simple downscaling technique. For precipitation, this is one of the downscaling techniques very commonly used. What is known as change factor. Okay. The change factor, as the name indicates the change that take place with reference to the past. So you can see change factor is computed as a ratio of what is observed, what is observed in the future to what is observed in the history. Okay, historical value. So the numerator is future value and denominator is historical value. Now, this X here indicates a quantile. It means we did this, say, typically, for example, if I take like rainfall, let's say. Now, the rainfall, if I take the past rainfall of, rainfall, it has got its own distribution, equivalent distribution. So what we try to here is I take different quantiles and then I'll take for that particular quantile, for example, 5% quantile means what I mean by quantile here is if I say 5% quantile, the probability its non-exceedance is 5%, 5.05, and probability exceedance is 0.95. If I take 50% quantile, it means the 50% chance it will not be exceeded, 50% chance that it will be exceeded. So if I take different quantiles, I'll find the historical value of that quantile and then the future value predicted by the GCM of the quantile and take the ratio, and that ratio we call this as a change factor. So we use this change factor. So I compute the change factor from the GCM predictions and then use this change factor to find out for another variable which I'm interested to predict what its value in future will be. I'll take the historical value and then multiply with the change factor in order to get the future value. So that's how we try to find out, use this change factor. This is a simple method for downscaling. It has got its own limitations, but but it is one of say for a short duration rainfall. I think among the various downscaling techniques, this is a better technique, and this is why we have used. Mostly, this technique is used mainly to downscale rainfall, short duration rainfall, as well as temperature. So we use this to do this, for both temperature as well as downscaling temperature as well as precipitation. And then to generate the future scenarios, we used what is known as K nearest neighborhood algorithm, which is KNN weather generator. It's a kind of procedure, statistical procedure, which actually it just try to do some kind of perturbation of the historical data and randomly generates the data scenarios for the future. So we use the KNN weather generator, and along with KNN weather generator and change factor, we try to generate the future scenarios of rainfall for Hyderabad city for different based on different GCMs outputs and by different RCPs. Now, why we use 24 GCMs? Again, maybe other speakers also would have talked about this earlier. Now, whenever you're trying to do this modeling of climate change, now GCM is a model which is trying to model the global circulations. Now, any model obviously has its limitations, and the model is based on certain assumptions and presumptions. So every model has its own limitations. Now, obviously, when you try to use a model to do a study, there's obviously going to be some uncertainty. So each GCM has its own capabilities. It has got its own advantages and disadvantages because different climate centers across the world have developed different GCMs based on their own analysis, their own capabilities, and so on. So every GCM has its own analysis, its own capabilities. So we don't know which of this GCM is better for our area or for our study area, or for our hydrological studies. So we try to take an ensemble of this GCM so that we can actually try to average out the uncertainties. Maybe some GCMs try to overpredict, some GCMs try to underpredict, the impacts. So we try to combine them so that there's an averaging out of these things. That's basically why we try to use an ensemble of GCMs. So that's what we did here also. We took 24 GCMs and tried to do an ensemble of this. And then we did what is known as REA analysis, which I'm just going to explain briefly next slide, to actually find the average of this 24 GCMs, because I need the final outcome in terms of an average of this. So this is what we try to do. This is a flow chart. This first part shows, this is the the first column here actually is just a conventional model, like is the stationary method we use. And there's a thing that I have already explained earlier to develop the non-stationary IDF curves. And this is what we try to do here as far as climate change is concerned. We say procure the GCM simulations for both historical as well as future periods, and then computed the change factor for each RCP scenario of two future. We divide total future period in two parts: 2000 actually 15 to 2056 and 56 to 2100, and then say we use the say day maximum rainfall series for difference using CF. We try to modify the maximum rainfall day, and then did the resampling using K and weather generator, and then based on develop the idea curves for different RCP scenarios of two future time periods. So this is what we try to do to study the impact of climate change on the IDF relationship. Okay, so we use a statistical downscaling called change factor along with KNN generator as a statistical method in order to generate the future scenarios and all of the future IDF curves for the city of Hyderabad. There's a just list of 24 GCMs that were used, and the center which has developed these models, the GCMs, and then what are the scenarios that are considered under each of this. So as you all know, there are four different scenarios: 2.6, 4.5, 6, and 8.5. We indicate what is going to be the say predicted CO2 emissions at the end of the century. This RCP is based on that scenario. I think all of you know 2.6 is the most optimistic thing, where we expect that at the end of century the emissions becomes 2.6 watts per meter square, whereas 8.5 is the other extreme, whereas pessimistic view, where it's going to be on higher side. So this reliability ensemble average method, what is known as the REA method, is actually tries to average out the uncertainty from each of the GCMs. So we take the projections, and then we assign weights to GCMs based on the RMSE, that means root mean square error. What we do is we compare the GCM simulation for the historical period, and then based on this comparison, develop the RMSE. So based on the RMSE, we give the weightage for different GCMs, and then do an iterative process so that this GCM, this RMSE is updated continuously, and then finally we evaluate the convergence criteria, and then convergence weightage, and then take the weighted average of all the GCMs to develop the GCM of the future simulations. This is how the change factor of the REA has changed over 2015 to 56 period. This shows a different percentage how the REA factor is. So what you observe, why I've shown here is you can see that REA, this change factor is maximum for higher percentage rainfalls. That means higher percent rainfall indicates that this is say less frequently occurring rainfall or more extreme rainfall. So you find the REA is small for short duration rainfall, but becomes larger for extreme rainfalls. And based on that, we develop the IDF curves for the say future scenarios. So you can see these are the zoomed values. You find that all the four we compare observed, non-stationary, and then say the IDF developed for 2015 to 2056, and then REA developed from 2057 to 2098. And based on that, you find that by 2057 to 2098 period, the intensity of rainfall is going to be much higher than what we are observing today. So there's continuous increase. Whereas this 2015 to 2056 more or less coincided with what we got from the non-station analysis of rainfall. So they are matching almost. But 2057 to 98 period, the rainfall is going to be more extreme. So this is a typical example to show how we can take into account the impact of climate change on the extreme rainfall in urban area. And as I mentioned already, this idea curves become the input to the studies that we make in urban areas to actually study the this flooding. Anyway, because of paucity of time, I'm not able to show this, but actually what we did here is based on this idea curves, as I said earlier, we try to disaggregate this and then convert into shorter duration rainfall also, and then use this along with the hydrological simulation like HMS in order to develop the flood hazard maps of Hyderabad city. In fact, that's part of the PhD work of another student of mine who just about defend his viva maybe in another 1 week or so. We try to develop the hazard maps, flood hazard maps, how the flood hazard is going to increase, flood hazard is going to increase in the future because of climate change. So this is going to become input for that kind of study. So this we take as input the hydrological model and then run a hydrological model for the area and then find out the flood inundation and then how much area is going to get inundated and then based on the risk or analysis we can perform. So, so any study that is to we said to understand the impact of either urbanization or climate change, I think has to follow one of these methods. So either you try to do model the non-stationarity or develop the impact of climate change on the IDF curves. IDF curves they become the input of this. So before I conclude, I just like to finally to talk about the challenges that we face in the urban areas. Okay, we try to understand how the climate change or urbanization is impacting the IDF curves. But how do we incorporate it in our risk analysis? Because when we try to develop the say designs, we have evolved to some written period. So, for example, I designed this for 2 years written period or 5 years written period. These are based on some kind of economic analysis. So there must be, I think, under the climate change, do we take the same risk or do we also have to change the risk at which we design the various structures we have? So we need to, I think, risk cost analysis we have today do analysis, risk cost analysis, and then revisit the design criteria that we have evolved over years, like this kind of structure designed for this kind of written periods. So this, I think, is very essential when, especially in urban areas, and how what is risk and then how to do a risk cost analysis and find out what should design criteria. We have to modify our design criteria of changing return levels into our design procedures. I think these are challenges, key challenges. So a lot of people have done already studies on the impact of climate change and how it's going to influence the extreme rainfall. But how we incorporate results into our design is what is now has to be taken up, and this is going to be a challenge of the future studies or future research that takes place. So with this, I conclude this my talk and thank you. As I close this, I just like to uh, give a quote in fact, end my lecture with a quote. What is required is a fundamental change in how we view flood management, flood defense, where we protect ourselves to one of resilience, living with and making space for water and the opportunity to get more from less by seeing all forms of water as providing multiple benefits. There's a quotation that I borrowed from a report submitted by Commission of Inquiry into Flood Resilience of Future, titled Living with Water, submitted to House of Commons in London in 2015. What means is, okay, till today, we always talk about flood as a nuisance, and we always wanted to defend ourselves against flood by trying to dispose the flood as early as possible. But we have to look at this as an opportunity, and maybe this flood, uh, we can try to make use of flood as a resource. Don't look at flood as a nuisance, but look at flood as a resource and see whether we can try to use this as a resource and improve, and in fact, protect ourselves from flood. At the same time, use this flood as a resource and improve our water availability. I think this is what it means. So with this, I conclude my talk and thank you very much for giving me this opportunity.
Yeah, thank you, sir, Professor Umamahesh garu. Audience can have any doubts or questions or clarifications, please. Sir, there is a question from Sridhar Curry.
Yeah. Yeah, I can see that whether Chennai floods of 2015 are man-made or natural. Uh, okay, it's difficult to say. It's both man-made or structure. I think I have read a report submitted by a group of people from IIT Bangalore, IIT Bombay, and IIT Chennai who have done studies. But what they say is one is okay. Natural is the rainfall that occurred on that day was too extreme, very extreme rainfall. I think it has got written period of 200, 250 years of rainfall, written period rainfall. At the same time, I think there's a, say, man-made, it's also a man-made disaster because what I understand from the report is that the operation of the various utilities that are present along the drains have not been properly done. And that also could have resulted more damage. So we cannot control rainfall, but at least we could have controlled damage if these reservoirs which are there could have been managed properly. Okay, I think the previous question, also second part of the question, talks about drainage systems. I'll talk about two things here when I talk about Indian drainage system. One is, I think most of the time when we develop a new urban area, we give least importance, least priority to the urban say drainage system. In fact, I even feel that this concept of smart city is also drainage is given less importance. Unless you have a proper drainage system, I think we'll not be able to make a city more livable and more smart. And obviously, most of our drains, even if they are there, they're not maintained properly. Uh, yeah, how to convert floods from a threat to a useful resource? I think that is how we can say we talk about rainfall harvesting and various methods of rainfall harvesting have been discussed. In fact, most of the time we try to implement them in rural areas in terms of watershed projects and so on. But same thing can be done in cities also. Maybe government talks about infiltration ditches, but infiltration ditches are not the only way in which you can collect water as a resource. There are different ways in which you can actually recycle the storm water and use it for various things.
Yeah, Professor Sudarshan Rao, thank you very much for joining us in this program. Sir, Umamahesh garu, Professor Sudarshan Rao is a professor in
Yeah,
civil.
I know Prof. Sudarshan. I know Prof. Sudarshan. We have met number of times. I'm surprised to see actually his question here because I thought I was surprised to see
Yeah,
that he met the participant here.
it is. He is
How are
following,
you?
Professor Sudarshan Rao is following very closely all the lectures.
Okay.
Any questions? Sir, there is one question.
Yeah. What are the various platforms software download and GCM model output? No, most of GCM data is freely downloadable. In fact, there I think say if you actually start searching in the net, you will find links for downloading GCMs. Every uh, say climate center has its own download link for downloading GCMs. And in fact, there's a website which actually tries to combine all of them. We have what is known as CMPF5 from where you can download any GCM. The only thing is the GCM data is usually because you have used data, it is a different format. You need some software to actually convert into the format in which you can use it. I think there are software both in MATLAB as well as R to actually do this kind of transformation from the GCM output, the format in which the GCM data is available to the format in which you require for your analysis. Okay, I think a lot of people are interested in knowing different floods, whether they are man-made or natural. No, most of this we cannot. I think it's very difficult to separate out this thing. In fact, many of these floods which have occurred recent past are combination of both. See, we cannot say nature it's not complete nature's fault. There's an extreme rainfall, but how we get prepared for that also is important. So most of this recent flood events, whether Chennai or Kedarnath or I think Mumbai also every year we're occurring. All these are like a combination of these, both man-made as well as uh, human. How to get the long-term hourly daily rainfall data from MD? Is it affordable? Uh, Obviously, I'll say, as per my experience, it's no. In fact, for Hyderabad city, we purchased that 42 years of hourly rainfall data of only one station, that is Begumpet. it costed us around 42,000. Okay. But as far as gridded rainfall data is concerned, is more affordable, because I think if you just pay around 5,000 rupees, you can get 0.5 degrees or 0.25 degrees rainfall data, gridded rainfall data for I think more than 100 years, because 1901 to 2011 or so. So that is easily obtainable. They send you in CD. I think now they made it even freely downloadable also. I don't know, but we purchased it with 5,000 about 5 years back.
Yeah, if no further questions, I would like to thank Professor Umamahesh garu, spending a lot of time in preparation of the slides, and also spending almost 1 hour 45 minutes presenting his research work to all the audience or participants. Sir, most of the participants are into the water sector, either they are civil engineers or MTech scholars or PhD, and the faculty members across the different engineering colleges. So I think your lecture, your detailed explanation on different aspects of the GCMs, and then extreme value analysis, log normal Gambelti, analysis systems, then IDF, intensity, duration, frequency curves. It will help them a lot for their research work, or it may be project work. So in that way, in that sense, it is most valuable lecture for them. And
Thank you. Thank
on
you.
behalf of, sir, on behalf of participants and on behalf of Department of Civil Engineering, Andhra University, I would like to thank being with us for this hour in the evening and spending your expertise on this, and also thank from on behalf of this Science City hosting this program. Thank you very much, sir. In future, we'll be meeting somewhere in conferences or like these webinar programs. I only request to please extend your hand so that we can do some conferences work like this.
Sure. Thank you very much for giving me the opportunity, and I enjoyed my interaction. Maybe I hope this my talk was useful for the participants, at least some of them
Definitely,
who
sir.
are
They will pick some idea out of your research work. They start doing project work. Yes, maybe they can pick one parameter for MTech project. It is most your efforts are well paid.
Thank you.
Right, sir.
Thank you very much. Thank
Thank
you.
you, sir.
Thank
Namaste.
you.
Charan garu.